The paper presents a value-oriented point forecasting approach for sequential energy dispatch problems, focusing on the integration of renewable energy sources. Traditional forecasting methods overlook the operational value of forecasts, leading to suboptimal operation costs. To address this, the authors propose a forecasting approach that aligns the loss function with the overall operation cost function, thereby reducing operation costs. The forecast model parameter estimation is formulated as a bilevel program, where the upper-level objective is converted into an equivalent form using the dual solutions obtained from the lower-level operation problems. A novel iterative solution strategy is proposed to solve the bilevel program, showing that the upper-level objective is locally linear regarding the forecast model output and can act as the loss function. Comparative analysis with commonly used statistical quality-oriented point forecasting methods demonstrates that the proposed approach results in lower operation costs. Furthermore, the approach is more computationally efficient than traditional two-stage stochastic programs. The increasing penetration of renewable energy sources has led to a surge in renewable energy forecasting research, motivating this work. The proposed approach has the potential to improve the value of sequential power systems operation, where the value of forecasts is evaluated by multiple temporally correlated operation problems. A novel value-oriented forecasting approach is introduced for optimizing the day-ahead renewable energy source (RES) schedule in centralized energy dispatch problems. This method aligns the loss function with sequential deterministic operations and employs an iterative solution strategy for parameter estimation during the training phase. This approach improves computational efficiency and applicability to existing deterministic operation structures, surpassing two-stage stochastic program methods. In a centralized virtual power plant (VPP) operator setting, the goal is to balance total demands at the lowest cost through economic dispatch. The VPP operator manages a group of assets, including RES, slow start generators, and flexible resources. The value-oriented forecasting framework is designed to obtain point forecasts of RES that align with the sequential deterministic operation paradigm. A bilevel program is formulated for forecast model parameter estimation, where the lower level solves the day-ahead and real-time dispatch problems with the forecast acting as a parameter. The upper level optimizes the model parameters along with real-time decisions, establishing a relationship between the forecasts and optimal operation solutions. Unlike previous works that rely on linear regression models, this approach enables a wide range of regression models to serve as forecast models, expanding beyond previous limitations. Furthermore, the loss function exhibits local linearity with respect to the forecast model output when the operation problem takes the form of linear programs, facilitating the use of advanced regression models as forecast models and improving overall performance. The proposed method stands out for its enhanced computational efficiency and applicability to existing deterministic operation structures, compared to two-stage stochastic program methods. With the RES forecasts obtained by the proposed framework, the operator only needs to solve deterministic problems at the day-ahead stage, while informing the day-ahead operation with future real-time cost by the improved RES schedule. In the context of virtual power plants, VPPs, dispatch models play a crucial role in optimizing power generation and ensuring a stable grid. This research paper presents a sequential framework comprising day-ahead and real-time stages to dispatch VPPs. In the day-ahead stage, slow start generators are scheduled for each time slot, considering a single renewable energy source (RES) forecast. The objective is to minimize the operation cost of slow start generators, subject to operational limits, ramping constraints, and power balance constraints. In the real-time stage, the operator dispatches flexible resources to compensate for power imbalance caused by forecast errors. The real-time dispatch problem is formulated as a minimization problem, where the objective is to minimize the cost of flexible resources outputs, subject to upper and lower bounds on flexible resources output and ensuring that the deviation between RES forecast and realization is addressed. 3 dispatch models are presented: deterministic, stochastic, and improved deterministic dispatch. The deterministic dispatch model schedules slow start generators in day-ahead, considering a single RES forecast, and addresses power imbalance in real time via flexible resources. The stochastic dispatch model solves a two-stage stochastic program in day-ahead, anticipating the impact of res schedules on real-time operation. The improved deterministic dispatch model leverages a strategic res schedule within the deterministic operation framework to approach the performance of stochastic dispatch. Notably, forecasting products are required at the day-ahead stage, where operators need to predict a single value for the res generation. The realization of res generation is approximately informed close to the time of delivery, allowing for an accurate estimate. The load forecast is assumed to be rather accurate, and the uncertainty is only from res. The integration of probabilistic forecasts into day-ahead and real-time dispatch models for renewable energy sources, res, is a crucial step in optimizing the operational efficiency of these resources. A two-stage stochastic program has been proposed to co-optimize the day-ahead and real-time operations, taking into account the temporal dependency between the two stages. This program aims to determine the res schedule and generation schedule, anticipating their influence on the expected real-time cost given any potential realization of the res. The stochastic program is formulated as a minimization problem, where the objective function includes the first stage cost and the expected second stage cost. The first stage decisions include the res schedule and generation schedule, while the second stage decision involves the flexible resources output. The problem is subject to various constraints, such as the res capacity, generation limits, and energy balance. In order to estimate the expected second stage cost in the stochastic program, operators must predict the conditional distribution of res realization given contextual information. This distribution is essential for accurately assessing the potential outcomes of different operational strategies. An improved deterministic dispatch approach has also been proposed, which optimizes the res schedule with the same objective as the two-stage stochastic program. This approach ensures that the res schedule aligns with the deterministic dispatch framework. A bilevel program is formulated to optimize the res schedule, where the upper level determines the schedule and the lower level solves the first stage and second stage problems separately. The bilevel program is formulated as a minimization problem, where the objective function includes the first stage cost and the expected second stage cost. The problem is subject to various constraints, including the res capacity, generation limits, and energy balance. By optimizing the res schedule with consideration of the second stage cost resulting from res uncertainty, the performance of separate operation models can be enhanced. A novel methodology is proposed for estimating the parameters of a value-oriented forecasting model, aimed at minimizing the expected operation costs of both first-stage and second-stage problems. The proposed bilevel program consists of an upper-level problem that determines the parameter theta v, and lower-level problems that repeat the day-ahead and real-time operations to obtain optimal solutions parameterized by the forecast id, tau. The upper-level objective function minimizes the average of the two-stage operation cost over d days, approximating the expected second stage cost by the cost under the support yd, tau. The lower-level constraints include the forecast model, bounds on the forecast, and the day-ahead and real-time operations. Additionally, feasibility conditions for the day-ahead operation, ramping constraints, and energy balance constraints are considered. The bilevel program is solved using a training set formed by historical contextual information and res realizations in d days, assuming unique primal and dual solutions for the day-ahead and real-time operations. The proposed methodology aims to learn a forecast model that maps contextual information to an improved res schedule, minimizing the expected operation costs of the two stages. By considering future balancing costs caused by res uncertainty, the methodology improves the accuracy of res forecasts, enhancing the efficiency of res integration and grid operation. The bilevel program provides a systematic approach to estimate the parameters of the value-oriented forecasting model, applicable to solving the stochastic bilevel program for determining the res schedule on a new day. The paper presents a bilevel optimization model for estimating the parameters of a forecast model used in day-ahead and real-time dispatch of renewable energy sources. The upper-level problem aims to minimize the average operation cost over d days, while the lower-level problem solves for dispatch decisions based on forecasted res generation. The lower-level problem is replaced with its dual problem, enabling the calculation of parameterized dual solutions. An iterative learning strategy is proposed for parameter estimation, where the model parameter is initialized and the forecast is redetermined with updated parameters in each epoch. The upper-level problem optimizes the model parameters using the parameterized dual solutions provided by the lower-level problem. The estimated parameter is then used in the operational forecasting phase to forecast res generation for each time slot on the next day. In the context of a virtual power plant, VPP, operator managing wind power, this page delves into the training phase of a neural network, NN, for value-oriented forecasting in sequential deterministic operation problems. The proposed approach employs an iterative scheme where forecast model parameters are updated based on parameterized dual solutions obtained from the lower-level problem. This method is compared to quality-oriented forecasting methods that utilize mean-squared error, MSE, or pinball loss as loss functions during training. A case study using wind power production data from 2012 and real demand consumption data demonstrates the effectiveness of the proposed approach. It results in lower average operation costs, operational advantages under large wind power penetrations, and computational efficiency. The use of multi-layer perceptron, MLP, as the forecast model is also discussed, with hyperparameters summarized in Table I. The performance of the proposed value-oriented forecasting approach is compared to 4 benchmark models, including 2 quality-oriented models trained under MSE and pinball loss, and 2 value-oriented models. This comparison highlights the significance of the proposed method in enhancing forecasting accuracy and operational efficiency for VPP operators. Optimizing wind power output for microgrids requires accurate forecasting models that balance accuracy and operational costs. This research compares value-oriented forecasting models with quality-oriented models, highlighting their differences in accuracy and costs. The value-oriented model, trained under a pinball loss function, demonstrates a significant reduction in operational costs compared to quality-oriented models, such as QA-E and QA-Q, despite having a higher root mean square error, RMSE. The value-oriented model forecasts less wind power production than quality-oriented models to avoid underproduction and reduce real-time operational costs. This approach leads to higher day-ahead operational costs due to lower forecasted wind power output, but ultimately results in lower overall operational costs by minimizing both day-ahead and real-time costs during training. The proposed iterative solution method is compared with other value-oriented forecasting approaches, such as VAL and VALO, demonstrating its effectiveness in reducing operational costs. Integrating advanced forecasting models, like neural networks, the proposed approach and VALO achieve lower average costs compared to VAL. In contrast, the quality-oriented model trained under mean-squared error, MSE, denoted as QA-E, shows worse performance compared to VAL, despite employing a more sophisticated model. The value-oriented forecasting model provides an operational advantage in optimizing wind power output for microgrids, achieving lower overall operational costs while maintaining acceptable accuracy. This is achieved through the use of a pinball loss function and an iterative solution method that integrates advanced forecasting models, making it a promising approach for microgrid optimization. The value-oriented forecasting approach is a pivotal method in energy dispatch problems, particularly in systems that incorporate renewable energy sources. This approach aligns the training of forecasting models with operational performance, leading to more accurate and efficient energy management. In the context of wind power, sensitivity analysis demonstrates that increasing wind power penetration levels results in cost reduction. This highlights the importance of integrating renewable energy sources into the grid for economic benefits. A comparative analysis with a stochastic program reveals that the proposed value-oriented forecasting approach exhibits lower computational complexity, despite slightly higher operation costs. This trade-off between computational efficiency and operational costs underscores the importance of balancing these factors when optimizing energy dispatch strategies. The application of this approach in real-world scenarios could significantly impact the efficiency and sustainability of energy systems, especially those reliant on renewable sources. As the global energy landscape continues to shift towards cleaner, more sustainable options, the value-oriented forecasting approach may play a crucial role in ensuring reliable and cost-effective energy supply. In conclusion, the value-oriented forecasting approach offers a promising solution for optimizing energy dispatch in systems with renewable energy sources. Its ability to align forecasting model training with operational performance, reduce costs with increased wind power penetration, and provide computational efficiency despite higher operation costs makes it an attractive option for stakeholders seeking to enhance the sustainability and efficiency of their energy systems. This research paper introduces a novel approach to value-oriented forecasting in electricity markets, focusing on integrating renewables into the operational framework. It presents an iterative solution method that combines predictive modeling with optimization techniques, allowing for more efficient and cost-effective decision-making processes in power systems. The proposed bilevel program optimizes both the forecasting model and the operational problem simultaneously, providing a comprehensive understanding of the interplay between forecasting and optimization. The paper emphasizes the importance of considering the operational context when formulating forecasting models, as traditional quality-oriented forecasting methods may not directly translate to optimal operational decisions. Instead, it advocates for a value-oriented approach that prioritizes minimizing operational costs over improving forecast accuracy. The proposed method is demonstrated through a centralized operation problem involving wind power, where it outperforms quality-oriented forecasting methods in terms of average overall operation costs, particularly under high levels of wind power integration. The computational efficiency of the proposed approach is also shown to be superior compared to stochastic programming. The paper highlights the potential of this novel approach to enhance the integration of renewables into the grid by optimizing both forecasting and operational decisions. This could lead to significant reductions in operational costs and improvements in the efficiency of power systems, ultimately contributing to a more sustainable and cost-effective electricity market.